Okay, hello everybody. Welcome to our joint bioengineering seminar series. Today we are hosting Rohit Kate, who is an associate professor in the Department of Health Informatics and Administration at UWM. He also has adjunct appointments in the Department of Computer Science at UWM and in the Clinical and Translational Science Institute at Medical College of Wisconsin. He received his PhD and Master's in Computer Science from University of Texas at Austin and Bachelor of Technology in Computer Science and Engineering from Indian Institute of Technology in Delhi. He has several research interests. One of them is applying natural language processing techniques to automate analysis of biomedical and clinical text. In this area, he has been leveraging available biomedical knowledge resources to improve techniques for extracting computer processable knowledge from clinical text. He also works on applying machine learning techniques to do predictive analytics for medical applications. Most recently, he has worked on predicting acute kidney injury and predicting cancer survivability using machine learning models that he is going to talk to us about today. Please join me welcoming Dr. Rohit Kate.
Thank you for inviting me and thank you for coming. So, and thanks for the introduction. And so today I will talk about predictive analytics and an application in predicting survivability across different cancer types. So, it was already said, so all my degrees are in computer science and my research interests are basically two categories, machine learning and natural language processing. So today we will talk about machine learning, and I won't be talking about natural language processing, that's another thing I do. And then my interest here is actually in applying these to biomedical and clinical applications as part of biomedical informatics. That's why I'm in the health informatics. So again, so I will begin with a brief introduction to predictive analytics, maybe 10-15 minutes. And then on the application for cancer survivability prediction. So what is predictive analytics? So it is building and using models to make predictions. And a prediction is usually when we say prediction, it means what will happen in future. But prediction here means kind of something more general, like you may be also predicting with some unknown value, like what diagnosis, what disease someone has, those type of things. So this prediction is more general than that. And it is a booming field, and I will quickly give some examples of its applications in various domains. So like in business, it is being used to like things like stock market prediction. You want to predict tomorrow's stock based on economic factors and past records, or want to predict price based on seasonal changes or customer demand, so that you have the best price that will give you maximum profit. Or you want to predict whether a loan will default or credit card transaction is fraud. So it has many applications in business. And in medicine, you can predict medical diagnosis, whether someone has a particular disease or a particular disease is present, or someone can get a particular disease, or whether someone will survive or recover. And the application we will talk about will be on predicting survivability or predicting dosage, like what should be the right dosage for a medication. So all these are applications of predictive analytics in medicine, and the list goes on. So these are just a few examples. And so that was business and medicine. It has many other applications, recognizing spoken words, handwritten characters, classifying documents, or classifying emails as spam or not spam. So the same techniques or the same predictive analytics can be used for various applications. Now, how do you do predictive analytics? Like, how do you make these predictions? If you can use a crystal ball. So that's one way to do predictive analytics. Or what you can do is you can manually build model. You can sit and kind of try to link all these factors and to make predictions, and you can manually sit and build a model like that. And thirdly, you can use machine learning. So that's what we will talk about. You can use machine learning to automatically build a model from past data to make predictions on new data. And so that's the most common way of doing predictive analytics. So what is machine learning? So it is automatically learning a model from past data to make predictions. And again, we will go into a little bit details of that. So technically it is called supervised learning, that is we are using some past data to make predictions or to learn model. There are also semi-supervised and unsupervised learning. We will be skipping that. So the little terminology, so what is being predicted is called target, and the data is represented in terms of what are called features, and we will see a few examples of that. And the pairs of features and target are called examples. And so in machine learning techniques, they learn relationship between features and target from training data or historic data or training or called training examples. So this is how the general picture looks like. You have training data, which is basically a pair of features and target. Again, the features you have to decide based on what the application is, and this is what you want to predict. So this is the training data that will go into machine learning method. And then there are lots of machine learning methods. We will see why there are so many machine learning methods, and it will then find pattern that relates features to target. And so that part is called training. And then once it is trained, you have the predictive model, and then you can give a new example for which you don't know the target, and you have to give them in terms of features, and the predictive model will give you a target prediction. It will try to predict the target, and that's called testing or evaluation. So just to give quickly some examples of features. Again, the features will depend on the task. So whatever the task is, features need to be appropriate to that. So if you are doing stock market prediction, your features will be economic factors, and you are trying to predict stock price. If you are classifying emails, features will be the words or phrases in the email, and your target is just classification, spam or no spam. And so for every application, you will have corresponding features and a target. The same techniques will work for all these applications. You just give different features and target. Again, for medical diagnosis, features will be patient symptoms, physiological factors, and so on, and you're predicting disease and so on. So training is system learns a model from examples of features paired with their corresponding targets, and testing is making predictions of targets on novel examples using their features. So the computer or the machine learns from example, that's why it's called machine learning. And this is opposed to humans directly encoding knowledge into computer. The second picture we saw, that would have been manually encoding knowledge. So machine learning, it learns from the data. So some broad benefits of machine learning. It's computer who is doing all the work. So a computer can work with thousands of features, and that may be overwhelming for humans to deal with. And it's not uncommon to have thousands of features for some application. But for humans to build a model with thousands of features is practically is kind of impractical. And then it can learn from millions of examples. Those pairs we saw, they could be millions. And again, that will be problem for humans to look into so much data. And finally, it may also find some relations between features and target that may not be apparent to humans. So that's also something these methods can pick up, and these are the benefits of machine learning for predictive analytics. So there is usually distinction between two classes of in machine or two tasks in machine learning. So classification means when you're predicting a particular when what you're predicting is a categorical thing. So it's like it can take 5 values or 2 values, survive or not survive, some nominal or categorical thing like positive or negative diagnosis. And regression is when you're actually trying to predict a numerical value like the stock price or energy level. So that's called regression, and that term is also used in statistics. But one thing to keep in mind is even if it is doing classification, it may predict numerical values, and that could be the probability or confidence of the classification. Someone will survive with 0.9 confidence or 0.7 confidence, that can happen there. And most techniques are actually have classification and regression versions. So machine learning can be looked upon as a function approximation. So you are trying to learn a function that takes features and input and gives and returns the target. And it could be viewed as, and the function approximation can be viewed as search through different functions. And because of that, based on what functions you use, what type of functions you use, and what methods you use to search for the right function or to do approximation, there are several machine learning methods. So they differ in what functions, what function representations they use, whether a mathematical function or a symbolic function. That's called language bias or restriction bias. And they also differ in what search algorithms they use. That's called search bias or preference bias. So we will quickly look at a list. Again, we won't be looking into these methods, but you can choose a numerical function or mathematical function, and then you get these methods. Or you can have symbolic functions and you get these rule-based methods, or there are these instance-based functions which work directly on examples, or there could be probabilistic graphical models. So that's why there are so many machine learning methods based on what representation you use that relate features to target. And then how do you search the best method? Again, there are different methods for that, and that's why you have more machine learning methods. So some use gradient descent, some use dynamic programming. That's why we have various methods. Now, given that there are so many machine learning methods, usually people ask, like, which is the best machine learning method? So I have this data, which is the best method I can use? And usually those who don't know machine learning well enough, they think like there will be like a future method that will be the best method, or whenever a new method comes, they think, wow, this is going to solve all their problem. But it turns out it's theoretically known that there cannot be one machine learning method that will do well on everything. There's no panacea type of thing there, and this is called no free lunch theorem. So this is just a counter example. If you insist there is a method that is the best method, I came up with this method that will just solve all the problems, you give that method to me and I can give you a data set on which it will completely fall apart. How can I do that? Whatever it predicts, I just flip their labels and see this is my data. So it will give like 0% accuracy. So therefore there cannot be one method that will do best on everything. So what do you do when you have a task? The best way is you experimentally try different methods and see which one works best on your task or data. So we saw each method has a different search bias and language bias. Whichever fits your data best, that method will do best. And experimentally is the best way to just find that out, which method works best. So we talked about you need features for machine learning methods. So it is not a trivial thing to come up with the right features for your method. If you come up with just arbitrary features which have nothing to do with target, there's no way machine learning method can do any good job. So besides which machine learning method you employ, the performance also depends on which features you use, and it is a skill to come up with the best features for a particular task, and that is called feature engineering. And again, as I said, if you don't give the right features, machine learning method will never be able to predict the correct target. If you just give random features which have nothing to do with target, it's not going to work even if you use one of the best methods. Okay, now I want to spend a few minutes in talking about evaluation in machine learning, and particularly because this will relate to what I will talk about later in the talk about evaluation of survivability. So you build your model, predictive model, and it is ready to make predictions. Then the question is, how do you evaluate it? How do you know one method is doing better than the other? Or how do you know when you actually deploy your method in practice, how well will it work? So that's your question to answer. So a most common way to evaluate machine learning methods or predictive models is through what is called tenfold cross-validation. The idea is you divide your data. Again, in your data you have the correct targets for those features or for those examples. You randomly divide it into 10 parts and use 9 of these for training your model, and then test it on the 10th part. And you know the correct target for those, and so you can know whether you did well or your method did well or not. And then you repeat that 10 times with different test set every time. So like this black is the one, so every time you have a different test set and you use the rest of it for training and that for testing, and then you average the evaluations of these 10 folds. You can in general have n folds, but 10 is the most commonly used thing. And what do we evaluate? So, again there are multiple measures like precision, recall, accuracy, but two most common ones that I will talk about, because the later part of the talk will be based on these, and these are commonly used in medicine as well. So, this is called sensitivity and specificity. That is what you want to measure. So, suppose we want to predict survivability, which will be the later part of the talk. So, sensitivity will be, out of all who survived, what fraction was correctly predicted to survive. So, that is sensitivity, and specificity is just the flip of that for not survived. Out of all who did not survive, what fraction were correctly predicted to not survive. That is just flip of that. So, and it turns out there is a trade off between sensitivity and specificity. So, you can very easily get 100% sensitivity if you predict everyone to survive. In that case, whoever survive you predicted correct. So, you get 100% sensitivity, but your specificity will be 0. And similarly, the flip of that, you can predict nobody to survive, your specificity will be 100 and sensitivity will be 0. So, so most machine learning methods give a confidence, as I said earlier, or probability on their prediction, and we are talking about classification here. For example, 90% will survive, 90% confident that a patient will survive, or 75%, and using different thresholds on this confidence, you can actually get different sensitivity and specificity. Like if I have a animation coming up. So, for every threshold you can get different sensitivity and specificity. That is the knob to control the trade off between sensitivity and specificity. And then you can plot an entire curve between sensitivity and specificity, that is called ROC curve, or receiver operating characteristic. The term comes from a signal processing domain. So, let me just show. So, again I am showing this picture because it will be again relevant later. So, suppose surviving is, I call that positive, and not surviving, or I call negative. And suppose I have these 7 examples, just to show a kind of a toy example. Suppose we have 7 examples, and these are the correct targets. And so, there are 5 positive examples and 2 negative examples, and then I apply my predictive model and I get these confidences. So, this example, my method says it will survive 0.99 with 0.99 probability, and so on, and I sort them according to their confidences. Then if I use threshold equal to 1, that means I will say someone will survive only if the confidence is more than 1, and in that case I am basically saying no one is going to survive. I am saying no to all of them. So, then again, as we said, specificity will be 100%, sensitivity will be 0%. Then I reduce my threshold, maybe 0.99. If the threshold is more than 0.99, then everyone will survive, otherwise not. And then in that case only this one is surviving, because the confidence is higher than that or greater than equal to that. So, I make correct P prediction here. So, my sensitivity goes a little bit up, specificity same. Same thing I can keep on reducing my threshold, and so this, as the threshold goes down, these predictions are going from P to N, and my sensitivity is going up and specificity will go down. And in the end is that case when I call everyone to survive and I get 100% sensitivity, 0% specificity. And then I can plot a curve between sensitivity and specificity, and this is and it will look like this. So, traditionally ROC curve is plotted between 1 minus specificity instead of specificity. That's the tradition. You get a curve like this. So, for that example you get this ROC curve. You have more points, you get more smoother curve. So, in general it looks like this. So, a predictive model will be something like this, and this is sensitivity and 1 minus specificity. So, this you get this point when you predict everyone to survive, you get this point when you say nobody to survive, and if you randomly say 50% will survive. So, when you just randomly you are doing that, so half of those who survive you will predict correct. That is why your specificity and sensitivity will be kind of at this point when you have 50%, at 0.5, 0.5. If you say 80% you will be there, And so this whole thing is actually a random baseline. If you just make random predictions with 10%, 20% to survive, you get your ROC curve will be this diagonal line. So a predictive model needs to do better than that, otherwise it's really bad. So that's the random baseline. In general, it will be a curve like this, and a normal predictive model, and you get this curve using different thresholds. And if you do perfect predictions, then you will be at this point. And there is something called area under ROC curve. This is one number that summarizes the whole performance. If you are doing many comparisons, as I will show later in the talk, you don't want to plot too many ROC curves. You just find the area under the curve, and that one number summarizes everything. The higher the AUC, the better it is, and a baseline, random baseline gives you 0.5. So any model should be between 0.5 and 1. So we covered that predictive analytics introduction, and just to mention, there are several software available for doing predictive analytics. Some are open source and freely available. Weka is a popular one, especially in academia or research community. There are others too, and there are some other proprietary software, statistical type, and also you can directly program machine learning methods, and typically R and Python are kind of the ones which have good support for predictive analytics type of things. Okay, so we will move on to the next part of the talk, where we will actually apply that to a particular task, or it's like a case study on survivability across different cancer types. And this work is based on our these two recent papers, and this was work done with Ramya and Elham. So the way it happened was, we first did this for breast cancer, and we got interesting results, and then we thought whether the results will generalize across different cancer types, and so we did that for 9 other cancer types, and that was this paper. So I will talk about all that work. I want to begin with, again, as we said in the beginning, so my expertise is in computer science, not in medicine, so I want to make this disclaimer. So whatever you hear is not coming from a medical expert. Okay, so cancer doesn't need an introduction. It is the leading cause of morbidity and mortality worldwide. So in 2012, there were 14 million new cases in the world and 8.2 million deaths. And in US in 2014, 25% deaths were due to cancers, and that was the second leading cause after heart diseases. And the reason I have 2012 and 2014 instead of 2017 is because it takes time to collect data, and so these are the latest available data. So there are people have used used machine learning for several types of applications in cancer prediction. People have worked on predicting susceptibility, whether someone is likely to get cancer, or diagnosis, whether someone has cancer, or recurrence, whether the cancer will come back, or survivability, whether someone will survive. So that's the work that we will talk about, survivability. Now, for machine learning, you need some data set to train and test your things. So how will you get a cancer data set? So some of those who have actually worked in medical facilities or healthcare places, they have used detailed clinical and genomic information to do these type of things. But if you are not one of those, so the one thing you can use is this data set called SEER, which is actually publicly available, and it's very large data set, and I will talk about that. So it is very large, but it is less detailed. So it won't give you detailed clinical information or genomic information, but it is huge. So SEER is a big data for cancer. So SEER is a National Cancer Institute's program of surveillance, epidemiology, and end results. And under this program, they gather information of cancer incidences from different places in the US that represent 28% of population. It's funded by NCI and CDC, Center for Disease Control and Prevention. And this picture shows the areas from which there are registries in these areas, and the cancer data is collected from these, and the colors just show the who funds which areas. And so this is supposed to be very representative of races and ethnicities and all economic factors and so on. And but you can see Wisconsin is actually not included in that. So there's no registries here for collecting this data. So what is in the SEER data? So these are actually de-identified records of over 9.68 million cancer incidences that occurred between 1973 to 2014, and this is this year's release. They release the data every year with more incidences added. So this was in 2017, they went up to 2014, so it takes like 3 years to gather the data. So in that last release, there were like 500,000 new incidences. And it is available for free for everyone. You just need a sign, just need to sign a data use agreement and scan and email them, and you can they give you a password and you can download the data. So what is there in that data? So for each cancer incidence, so each of those 9.68 million, there are several demographic, cancer related and treatment related information, and it includes these. Some are kind of demographic ones, some are cancer related, some are treatment type, and the list is very big. I am just showing a small sample, and it comes with a patient ID. So although it is de-identified, but you can kind of track the same patient across different incidences using that ID number. So it is a great resource for generating cancer statistics. So many of the statistics, cancer statistics you hear, they come from the SEER data set. It's good for surveillance, whether a particular cancer is kind of becoming more is more widely becoming common, or someone is kind of going away, and those type of things. Whether a drug had a new drug had an effect in cancer survivability and those type of things. You can do cancer survivabilities, and you can build predictive models. So you got the data, you can build predictive models, and what can you predict? You can predict recurrence, whether someone got back the cancer, or you can predict survivability. And so in this work, we have done this. So people have done both type of things, and you can actually find survey papers like it has which they will talk about all type of work that people have done using SEER data or using other type of data. But recurrence and survivability are the most common ones. So we will talk about survivability. Now, how can you say someone survived cancer? Eventually everyone dies. So how do you say somebody survived cancer? The most common definition is if someone is still alive 5 years after diagnosis, then it is deemed they survived. Some use 10 years, but 5 years is the most common one. And why do you want to predict survivability? It's not just to tell the patient, but the healthcare providers can make more informed decisions if they know how likely someone is going to survive. If the survivability chance is very low, then they may go for aggressive therapies. So those decisions can be made if you can make good predictions on cancer survivability. So in our work, we build survivability prediction models using 3 machine learning methods. Those are the 3 naive based logistic regression and decision trees. We won't go into the details of those methods, and we did this for 10 most common cancer types in men and women. So as I said, we began with the breast cancer, and then we used 9 others. So these are the 10 cancer types we used. These are the most common in men and women. So the data we used for experiments, so again the SEER data set goes back up to 1973, but it's not a good idea to use that old data. Why? Because cancer survivability rates have changed dramatically over the years. So colorectal was 98 in 75, 67 in 2013. Breast cancer was 75% survivability in 80 and is 90% now. So it's not a good idea to use very old data. So we use the data since 2004, and the reason we chose that year is because the data's format changed on that year, so that was kind of somewhat convenient as well. And the second thing is the way survivability is defined for whether someone survives, is still alive after 5 years. We could not have used data for the recent 5 years, because then we don't know whether someone survived or not. So we have to exclude the recent 5 years, and we have to exclude everything before 2004. So these are the, so again, so we talked about what the features specific to the task for machine learning models. So these are the features we used, and again we are not medical experts, so we did not come up with these features. These are the features that had been used in past work, so we just use those features. Some of them are demographic type features like age, race, marital status. Some of them are cancer related, like these type of things, histologic type, grade, extension, behavior code, and some of them are treatment type, like radiation and surgery, those type of things. So these were our features, and they have been used in past work. And so how do you define if using SEER data, or how do you find in SEER data set whether someone survived or not? So there are 3 fields using that you can determine that. So there is something called survival months, if it is more than 60, and the vital status record, this is a field in SEER data set. If it is alive, then you know somebody survived. If it is less than 60 and cause of death is the same as the cancer type, whether it is breast cancer or colorectal for your data set, then you say it's not, the patient did not survive. But if they died of some other cause, then we just exclude that example. We have no idea, so we just we cannot predict they survive or not that particular cancer. So these are the features, and this is the target. And so this is used for training and evaluation. So this is what you want to predict using the features. This is the gold standard target. And so we saw that picture earlier, how machine learning works. So here training data will be the SEER data, the features will be the features we just saw, and target is survived or not, the way we just saw, we compute it. And then we train the predictive model, you give cancer features for any new example, and it will make the prediction somebody survived or not. So as I said, this has been done before by others, but one thing common in all those methods was all of them built just one model for all the stages of cancer. They built one model for all stages of cancer, although they use the stage of cancer as one of the features. As we can see here, stage is actually a feature and that everyone used it, but the model was built for all of them together. And they were also evaluated on all stages together, and that's what we did differently. So they did not distinguish between different stages during training and testing. So what are the stages of cancer? So cancer incidences are assigned stages based on tumor size and extension of the spread, and there are different staging systems. It's called, one goes like stage 0, 1, 2 and so on, another is called TNM staging, and third is called summary staging, summary stages. And this is the one that is directly given in SEER, so we use that as the staging. So in situ means the cells, the cancer cells are confined to the layer of cells in which they develop. Localized means it is limited to the organ. Regional means it has spread to nearby lymph nodes, and distant means it has gone to other tissues and organs. And the survivability rates kind of go down as the stages go up. Just to give an example, this is for breast cancer. So these are the survivability rates of different stages. So in situ it had almost 100%, and as you go to higher stages, the survivability rates go down, and distant had very poor survivability rate. And this was the distribution within breast cancer. So given the in situ stages, this is true for all cancer types, not just breast cancer, it's almost 100%. So we decided not to use them for predicting survivability, because it's trivial to predict survivability. It's like you predict survive and you get almost 100% there. So it's not beneficial to predict survivability for that stage. Okay, so for each cancer type, we built 2 types of survivability prediction model. One is called joint, in which we train our model using all the stages together, and that's what they had used in past work. And then we call stage specific models, in which one model is trained for each space, and that's what we did in this work. Let me show you in the picture. So this is our training data. It has incidences of localized, regional and distance, all of them together. Again in situ we throw them away, and then we train using machine learning method, we get one joint prediction model. That's the joint model that everyone had used before. This is what we did differently. We use only localized data and build a predictive model just for localized. only regional and for regional, only is distant and for distant. So we built stage specific survivability prediction models. So so you can train all jointly or you can train them separately. Besides that, you can also evaluate them jointly and evaluate them separately for both joint as well as stage specific. So I will just show the pictures. So if you have joint model, so this is trained, already trained, you can test on all of them, all the examples of all the 3 types, and you get one AUC number for all the stages. And that's what everyone had reported in the past work. Or you can do, you can test them separately on each regional, localized and distant, and you get 3 AUC numbers. And this is again the same joint model. So you can test them separately and you get 3 separate numbers. The same thing is true for stage specific models as well. You can test them separately, and when you are testing on localized, you will use the localized model. It was trained just for that, and you get these 3 numbers. And you can also combine the results and just give report one AUC number. Just combine all of them, although they were tested separately with separate models, you can combine to get one AUC. So you get these 4 AUC for both joint models as well as for stage specific models. So I will show some results, and again in the paper we have like 3 machine learning methods for 10 cancer types. So there are like 30 things. So I'm not going to show the 30 tables. I will just show some specific ones. So this is naive based model on breast cancer. So this is the joint model, and this is the stage specific, and the bold means they are statistically significant. And again, as I said, you can have evaluate them on all stages together and all stages separately. So the first thing that comes out from this is that stage specific models actually did better than joint model. So it's better to train these models specifically for those stages. We will talk a little bit more on that. The second thing you can see is the worst performance was on the distant stage. Actually the data for distant stage is very less, that's why the performance, the training is not complete. Like more data could increase this performance, and we would not have known that the worst performance is on distant if we had not evaluated them separately. So just by doing all stages you don't get that idea. Now what I found kind of really interesting was this. You look at the stage specific results, you are in kind of 70s and 60s, here also almost 80 and then 70s, but then you look at all stages together and the results are suddenly 88 and 87. So at first when we got these results, I thought there must be something wrong. So we checked into our code where something wrong is going on. Why? I mean this combined result should be kind of more like an average. That's the general kind of common sense. But why this is suddenly high? Why this is an overestimation? Then we looked at it more carefully, and it turned out when you evaluate on all stages together, it actually definitely leads to overestimation. And I will quickly try to demonstrate why that happens. And keep in mind that's what most past work were reporting, just the AUC on all stages together. So again we saw that diagram or that animation on changing the threshold and getting different sensitivity and specificity. So just consider this baseline model, which I call stage sort baseline, and this will illustrate why that is an overestimation. What I do, so I have these examples to make predictions on, and some of them are localized, some of them are regional, some of them distant. I just make random confidences on each example, but in such a way that all localized ones have higher confidence than regional ones, and which in turn has higher confidence than distant. And I know myself that localized has better chances of survivability, and then followed by regional, followed by distant. So I just sort them. So within localized the predictions may be random, but the confidences are such that these are above these and these are above these. So if I predict, so if my threshold is such that I predict all localized stage patients to survive and the rest not to survive, I get this sensitivity and specificity. It doesn't look that bad. And similarly, I can get other numbers as I go along this. I will get different numbers, but at that point I will get this. I go down below, and then I have like very good sensitivity and a little less specificity. And then I can plot an entire ROC curve, and find its area under ROC curve AUC, and that actually turns out to be 0.726 on that breast cancer data. It was 0.726, and that doesn't look that bad. And if you plot it, this is the stage sort baseline. So these are those 2 points, and another point is here that we just saw, and the rest you can get lines like these. This is ROC curve, and this is the diagonal baseline. So just doing nothing, just putting all the localized one before regional and those before distant, you can get very easily AUC of 0.726. And if normal prediction model will be somewhere here. So seemingly reasonable performance can be obtained when evaluating on all stages by exploiting their order of survivability. So that's why they were overestimations. So that stage sort baseline gave me 0.726 AUC. If you actually evaluate on localized itself, it wasn't doing anything. It was doing kind of random prediction. So it will be 0.5 and 0.5 and 0.5. And you can clearly see the case of overestimation. So evaluating on all stages together leads to an overestimation. So it's a bad idea to do, and the reason is because there's an inherent sorting of these stages. Survivability rates are sorted according to those stages. So evaluating on all stages together as done in past leads to an overestimation, and we actually found this to be consistently true for all cancer types and for all machine learning methods. So we have a table in our paper, and that is consistently true. So so that was for stage sort baseline, but predictive models can learn to rank localized, regional and distant stages in that order, and then for predicting survivability, and thus they also get artificial boost in performance. That's why they were all overestimations. So we recommend evaluating performance separately for each stage. That is more meaningful. If you are evaluating on all stages together, what you are saying is if someone is in a regional stage, you are predicting them to be survive better than localized and less than better than distant and less than localized. You are not giving them any more information. That's why evaluating on all stages together is not so useful. Okay, so the result I showed earlier was for naive Bayes for breast cancer. We get kind of similar results with other machine learning methods. This was the logistic regression. Again, this does better. Stage specific did better. For decision tree, stage specific did better. And now a few of other cancers. This is logistic regression for prostate cancer. Again, stage specific did better. And this is naive Bayes on lung cancer. This did better. So in general, the stage specific models did better than joint models. And keep in mind, so when I train joint model, I am using examples of all the stages, localized, regional and distant. So it actually gets more data to train, and usually more data means your performance will be better, but that's not happening in this case. What that shows is that the stages are sufficiently different from each other that adding examples of other stages does not help. So if you are trying to predict for distant summary stage, and then examples of localized and regional are so different from it that it doesn't help, doesn't improve performance on distant stage. So these results show that the most suitable model to predict survivability for a stage is the model trained only for that stage. Otherwise, you have mix of distributions and it doesn't do any better. However, we found a few exceptions to that where joint model actually did better than stage specific, and these were the exceptions for bladder, for distant stage, esophagus distance for those methods, and liver these. And you can see these are mostly for distant stages. And in all these cases, what was true was you have few examples of those stages. So distant stages usually have very few examples, which means the training is not complete. More data can give you better results. So you need more data to improve further. So you can plot a learning curve actually to show that. But when you have less data and the stages, the survivability rates of those cancers are such that the distant stages is not that different from regional or even localized, then it helps. So for these cancers, the distance survivability rates of distant is not as different from others, and they have fewer data. So we actually have a plot in which we illustrate that. So in these cases, including training examples of other stages actually help you, and that's why joint did better than stage specific. So here we have plotted, and this is all for distant stage. So this is the number of distance summary stage incidences, how many incidences are there in our data set. And you can see for liver, esophagus and bladder, we have kind of on the low side, we don't have enough incidences. And we have enough for those cancers. For lung, we have so many that it does not even fit in that plot. On x-axis, we are showing how different is the survivability rate of distant stage from other stages. So for liver and esophagus, the difference is not very high. For prostate, it is very high. So the localized is like maybe 99, I don't know, but 95% survivability, and distant will be like 20%. It's very high different. Here the difference is not very large. So those exceptional examples we saw where joint did better than specific, you can imagine this, you can kind of think about an imaginary line like this. So on this side, stage specific always did better than joint. When there is enough examples, or even if there are not enough examples, but the stages are sufficiently different from each other. But here is kind of sometimes specific does better, sometimes joint does better. When you have fewer examples and the stages are not different from each other. So to conclude, predictive analytics is a booming field with several applications, and SEER is a big data set for if you want to do cancer statistics or informatics or build predictive models. And the two things that came up from that the work we did was there are enough differences between cancer stages that it is better to build stage specific models to predict survivability instead of joint models as was done in the past. Secondly, predictive models should be evaluated separately for each stage, otherwise it leads to overestimation of performance. So thanks, and so I teach predictive analytics and healthcare course in spring, just for your information.
So we have a few minutes for questions.
Yes.
Your findings about specific models versus joint models is really interesting. It's also paradoxical, maybe, in the sense that you're taking out a feature, right? You're basically saying if we take one less feature and just look at that group without that feature in it.
Features is more on data, less data.
Less data.
Yeah.
And so could it be that you could look at other features and parse out the data even more and get even better prediction, like race or marital status or some other, for example, demographic or other features? Would that also help? If you could you parse out, could you instead in taking a one feature, you could look at other features as well and take subgroups, that this subgroup training for that is better for a given regression analysis.
There are two things. One is we are using the same features for all of them, for joint models as well as for stage specific. The features are same. It is just the data, like for the joint, for the stage specific, we are not using the training data of regional and localized if you are training for localized. But the features are exactly same. Like but
the stages for all the training sets, the stage value is the same for all of those features, for all of those examples, right?
Yeah. And the second thing is, so what you are talking about is called feature selection. So that is something that can be done. But given that we had like 16, 17 features, so feature selection is kind of useful when we have like hundreds of features, and then instead of confusing the method with so many features, you kind of select just a good set of features. But we already have like 16, 17 features, and those methods are kind of good for those. So I don't think features there will help. Grouping features will help.
Well, follow on his comments. Actually, I have the same comments. So what he mentioned, you take out one feature is in your joint model, stage is one feature. Mm-hmm. In your separated model, stage is
so
not
that's
a
the feature is not being used.
Yeah.
Is the same value for all of them.
Yeah, that's right. So following on that, so you might be the expert or some other expert coming to the problem and look at that, hey, why don't we do stage specific, so that then you do this work and you find the difference, you find the impact, that's great. Mm-hmm. But fundamental question would be, is there any way from data, not from expert, then you look at that and you say, hey, this feature maybe is more important than stage. You see what I mean? So maybe what you can look at is the joint model. So I would bet that if you look at the joint model, then you're going to find that stage is overwhelmingly important for your prediction. Then you're going to say that, okay, if this one is overwhelmingly important, then of course that's what you should overestimate because you have this one precisely given, then predict that right. So maybe if you look at the joint model and you find something even more predominant than stage,
So
then you
if-
take that out.
So if I get your question right, you are saying that instead of stage, if there could have been any other feature,
Yeah.
and if we make specific models with respect to that feature, we get the same effect.
Yeah.
So the thing is, I actually tried on all those features, if that helps, but this stage was the only one that was actually helping. And I think the reason was it is very clear the survivability rates are very distinct on that.
Well-
Usually on other features, that wasn't so much true for other features.
Or maybe I should rephrase that. At least if you go back to a joint model, and you can look at, I don't know whether you can look at how like dominant the stage is. If you found that stage is the most dominant feature, then certainly you can tell, okay, this one, if I take that out, then I'm going to get more detailed information.
Yeah, so we actually had in our paper we had plot of information gain for all the features, and so stage is kind of it's not the most important one. There are others which are more important, and the interesting thing we found was that the value of those features was how important those features are actually dependent on the stages. So for some stages, those site-specific surgery code and some of those were very important for say distant stage, and other features were very important for the localized stage, and that's why these stages are actually very different from each other,
Okay.
and that's why we got performance like that. Yeah. Yes.
Physician and see if this capability of predicting will help in any way the intervention, like the therapeutics, or the prognosis of that, that specific cancer type.
So I would love to collaborate with an oncologist, and actually I tried to make contact, so it may still happen. But it is a very good question. So many people like me in machine learning, we get a data and we make predictions, and then the question is how good it is for them. Another thing is they can actually tell us that instead of predicting that, if we predict something else, that will be more relevant for that.
And like at what specific time point would that intervention, like an
Yeah,
combination of
yeah.
radiotherapy or whatever,
Yeah.
will help the prognosis? I think that's the most important.
Yeah.
Based on these predictive models,
Yeah.
how can you do the intervention?
Yeah, it will. The best thing will be to have collaborate with some oncologists to do these type of things. Yeah.
Okay, I know someone there.
That will be good.
Okay, thank you very much.